the space webinar attendees, e-attendees today to coming to join our webinar today. So we're honored to invite Prof. Chul from KAIST Korea to give us a wonderful talk today. And the title will be Optimal Transport-Driven CycleGAN for Unsupervised Learning in Inverse Problems. So let me quickly introduce to you Prof. Chul. So Jong is a professor of the Department of Bio and Brain Engineering, and also adjunct professor at Department of Mathematical Science of KAIST, Korea. So he received the bachelor and master degrees from Seoul National University, Korea, and PhD from Purdue University. Before joining KAIST, Prof. Chul was a senior researcher at Phoenix Research, GE Global Research in New York, and a postdoc fellow at University of Illinois and Urbana-Champaign. So Jong currently serves as the associate editor for many well-reputed journals, including IEEE Transaction Image Processing, IEEE Transaction Computational Imaging, and also he's on editorial board for MRI, magnetic resonance in medicine. He's also currently serving as associate editor for IEEE Transaction on Medical Imaging and a senior member for a senior editor of IEEE Signal Processing magazine. So Prof. Chul is an IEEE fellow. He's also currently the chair of IEEE SPS Computational Imaging TC, which is like most of our organizers are affiliated to, and also IEEE EMBS Distinguished Lecturer. Jong was the general co-chair for 2020 IEEE Symposium on Biomedical Imaging, ISB, and also he's a program co-chair for 2024 ICASP. While his group was the first winner of the 2009 Recon Challenge at the ISMRM workshop with the famous KT focus algorithm, and also the runner-up at 2016 low-dose CT ground challenge organized by the American Association of Physics in medicine with the world's first deep learning algorithm for low-dose CT reconstruction. And his current research interests including deep learning theory algorithms for a wide range of imaging and reconstruction problems, including X-ray, CT, MRI, and optics, ultrasound, etc. So without further ado, let us welcome Prof. Chul to give us this wonderful talk today. Thank you, John. I will pass the time to you.
Okay, great. Thank you very much for the kind introduction. It's really great, my honor to be here to present our work. And in fact, I'm a little bit nervous because actually this is more like a broadcasting worldwide. And also I noticed some of my students are here too. And anyway, so let's do my best. Okay, so the title of my presentation is actually Optimal Transport-Driven CycleGAN for Unsupervised Learning in Inverse Problem. So as you know, we are currently living in the age of deep learning. So deep learning has many advantages compared to the classical machine learning approaches. For example, in the classical machine learning approaches, we first need to do the feature engineering to extract the features to fit into the simple classifiers. On the other hand, in deep neural network or deep learning, you don't need the feature engineering. You just feed in the raw data, and then your network automatically extract the features and design a classifier. Because of this simplicity, the neural network has been successfully used for various scientific discovery and the computer vision and all other applications. For example, in the medical imaging area, which I'm working on, so the neural network has been widely successful for the designing a diagnosis for the disease and also image analysis. But recently, the neural network has become a new frontiers for inverse problem. Nowadays, inverse people are realizing that using the neural network, you can directly form the images from the sensor data directly. And this is actually the main topic we're going to talk about. In fact, actually, before we talk about the deep learning approaches for the inverse problem, we need to actually discuss about the classical inverse problem approaches using the penalized least square. So for example, here, y is a measurement and x is a known image, and h is usually the imaging operator, like a Latent transform or Fourier transform. And usually this operator is ill-posed, and because of that, so we usually put the regularization term or prior informations. And then we try to find the trade-off balance between the two terms, and then find the solution that gives a trade-off between the two terms. So in fact, actually, this prior term gives some kinds of prior information and reduce the feasible set. Because of that, even though in the original airpose problem, there are a lot of solutions for the given measurement, you can actually reduce the feasible solution set. In fact, this kinds of parallel least square has been a classical approaches for the inverse problem. And for example, Tikhonov regularization or total variation or compressed sensing approaches belong to this class of parallel least square problem. However, the limitation of this one is, this is a top-down model. So usually prior information is designed in a top-down manner based on some mathematical principle. And also, this approach is transductive in the sense that it's not, or it's non-inductive. It's not inductive, which means that we need to actually solve this problem for every new measurement. If even though you solve this problem on particular measurement, you cannot utilize this kind of solution for other measurement. You need to solve the computation expense optimization algorithm for each measurement cases separately. So on the other hand, one of the most popular approaches in the neural network-based inverse problem approaches are fit-for neural network approaches. Here in this case, is Y is a measurement. And now, using the neural network, you are estimating the unknown images. Usually, to estimate this one, you need to actually have a trained neural network to find the correct neural network weight parameters. And then at the test phase, if you're given new measurement, then you can automatically obtain the image. So as you can see, this is a very most simplistic and also very fast reconstruction method for the inverse of using the neural network. However, in order to actually do this kinds of approaches, you need to train the neural network with a lot of data, especially you need to train this one using the supervised manner. On the other hand, recently there are a lot of progresses in the different kinds of approaches. For example, model-based approach and plug-and-plug approaches has been extensively investigated among the inverse problem community. Here, the idea is very similar to the penalized least square. We have a data fidelity term here, and there is a regularization term here. But now the regularization term is now obtained using the neural network. In fact, this neural network Q is a denoiser, and in fact, this regularization term gives a penalty to the noise term, and it tried to find the solution of that one. Because this is a similar to the penalized square, you need to actually solve this problem in an iterative manner. And there's a denoising step and image estimation step. So the nice advantage of this one is, because this is actually inside of the iteration step, you don't need a very big neural network architecture. So you can actually use a smaller CNN. And furthermore, you don't need to have a lot of training data. You can actually, even the fewer training data, you can actually obtain this image very well. But still, the neural network itself is trained in a supervised learning manner. And furthermore, you need to solve the iterative optimization algorithm again. So that means the nice thing about the fit-for nature of the neural network is gone in this kind of approach. On the other hand, another very important approaches people are investigating is a deep image prior model. Here, this is actually originally proposed for the computer vision applications. Now, this is only consists of the data fidelity. We have a Y measurement here, and this is H is the image operator. And now, instead of X, you are now estimating the you are now using the neural network. Now, the goal is, given the measurement data, you're estimating the neural network parameter. In fact, in this approach, one of the nice things is CNN architecture is used as a regularization term. And furthermore, in this case, you don't need to train the neural network. So this is a pure unsupervised learning method. That's actually one of the nice things about this. However, one of the important limitations of this approach is, in order to solve this problem, you need to actually train the neural network using the measurement data. So it requires a quite expensive computation. It's even computationally expensive than the penalty least square approaches. So the question is any kinds of approaches that we can, it's better, it's a still unsupervised learning manner, but still we can implement in the feed-forward manner. So that's actually the thing we want to address. In fact, this problem is unsupervised learning problem is very important. This slide is taken from the Jan LeCun's famous keynote talk in several conferences, including the ICIP in 2019. And here he mentions that machine learning problem itself is like a cake. And among them, reinforcement learning is just like a cherries on the cake. And the supervised learning is like the icing of the cake. But the main body of the cake and the journey of the cake itself is basically unsupervised learning, which means that the most of the machine learning problem, the most of the important part of machine learning problem is unsupervised learning, and that means we need to actually have some kind of systemic way of doing the unsupervised learning. In fact, this is especially more important for the inverse problem, because inverse problems, there are a lot of problems that supervised learning is difficult. For example, let's think about the low dose city problem. In this case, in the supervised learning framework, we need to actually have a matched high resolution, high dose images and low dose images. But usually it's not possible. Usually it's very difficult to acquire low dose and high dose from the same patient, because they increase doses, and usually IIB does not prove those kinds of experiments. Furthermore, in some other application, like for example, cardiac imaging like this, in these cases, people are obtain the multi-phase of the cardiac data, for example, but with the dose modulation. For example, in these cases, it's very low dose, and in the diastole phase, it's high dose. But the problem is, in order to do the learning, supervised learning, this heart image and this heart image is different because of the heart is moving. So because of that, supervised learning is not possible. Furthermore, let's think about the metal artifact removal problem in MR or CT problem. For example, in these cases, in order to do the supervised learning, you need to actually have a same body part without any matter and the same body part with the matter. But in fact, that's not possible in the ordinary situation. So it's difficult to obtain the paired measurement data. Now, in this example, this is coming from the remote sensing application from the satellite imagery. So here, sometimes depending on the sensor noises, there is some kind of structural noise patterns here. But the problem here is that you cannot obtain the noiseless images at the same spot exactly at the same time. So because of that, so supervised learning is not possible. For example, in the bioimaging application like a microscopy for blind decomposition problem, in these cases, there is no ground truth images, so it's actually difficult to do the supervised training again. So because of that, we need to actually design some kinds of unsupervised learning to address this problem. This is actually our geometric view or proposal for the unsupervised learning. So this is given in this way. For example, here, now Y is the space of the measurement, and X is the space of the unknown images. Now this purple dot is actually the measurement from some of the images you obtain in this Y domain. And now, and this black dot is actually the unmatched, unpaired images in the image domain. Now the goal is actually the inverse solution is try to find mapping from this measurement to this image domain, especially in this manifold. Now this is actually based on some kinds of nonlinear function d theta. Now this probability distribution nu is now transported to the probability distribution of mu theta, which is depending on the parameter theta. And on the other hand, this unknown image, which is matched with this, and this is also based on some kind of Ford physics to map to the measurement domain. Now, this is again, the probability distribution mu is now mapped to the probability distribution in the Y domain parameter is phi. And now the question here is now, in order to actually have a correct unsupervised learning, the distance between this mapping and this distribution, the probability distribution, the distance between two probability distributions should be minimized. At the same time, this is the same. So the goal of unsupervised learning is basically minimizing the distance between two distributions in the measurement domain as well as in the unknown image domain. In fact, this idea is actually inspired from the geometric pictures of the GAN, the generative adversary network. In fact, this figure is coming from this literatures here. So what you can see here is like this. In the GAN literatures, we are now generating, for example, face images from the Gaussian noises. Here now the Y is now spaces for the Gaussian noise with the probability distribution of nu here. Now this probability distribution is transported using the generator G theta, which is mapped to the mu theta in the image domain X. And now the outpoint is actually the real face images, for example. Now the goal is now try to minimize the distance of this synthesized probability distribution and the real measurement, real face image distributions. So the goal is minimizing the distance under the constant this is actually transported from these original measures here. Now, in this sense, that the important concept we need to actually understand to actually utilize this kind of geometric view is a notion of the distance in the statistical sense. This is so-called the statistical distances. And the statistical, in the machine learning literatures, there are two types of statistical distances which are quite often used. For example, one of the popular things is divergence, especially F divergences. For example, Ka divergence is one of the examples of this. Ka divergence or Janssen divergence is actually one of the examples of the F divergences. And another thing is a Wasserstein matrix. For example, Wasserstein 1 matrix is given by the norm and with respect to the joint measure, joint distribution. In fact, what happens is if actually minimize the generated GAN under using the F divergences, we end up with the original GAN architecture or F GAN architectures as a dual formulation. Similarly, if actually minimize the distance using the Wasserstein 1 matrix, then it ends up with the WGAN architecture, the Wasserstein GAN architecture. Now here, which kinds of distance measures is useful? In fact, there is a differences between the two measures. For example, here, this Wasserstein 1 matrix or Wasserstein matrix itself is a real matrix. That means it satisfies the four property of the matrix: non-negativity, homogeneity, so symmetry, or triangle inequality. On the other hand, divergence measure is actually only satisfying part of this kinds of matrix. So this is not a matrix, this is a pseudo matrix. But still, it is quite often used in machine learning literature, and especially in the probability, the information theory context as well. And also another limitation of the divergence compared to the Wasserstein matrix is divergence. In order to actually calculate the divergences, here, this is a function, or this f is a function, and this is d nu, and the mu is so-called a Ladon-Nikodym derivative. In this one, to make this one is available, then that need to be satisfied so-called absolute continuity. Absolute continuity means that, for example, the mu, the measure probability distribution is 0, for example, in this support. The nu should not be no probability located in this domain. So that means this A is not absolute continuous. On the other hand, the B is an absolute continuous. But one of the main assumptions of distance divergence measure is nu should be absolutely continuous with respect to mu. That means usually in the machine learning cases, one is a real distribution, the other is a generated distribution. So we need to actually always guarantee this kind of situation, which is unlikely in many real measurements because we don't know the real distributions. So that's actually another limitation. So that's why we are interested in utilizing the Wasserstein matrix, because Wasserstein matrix is still useful even in those cases as well. So in order to understand the Wasserstein matrix, you need to understand the theory of optimal transport. Optimal transport is a classical probability discipline in the probability theory. It's actually interested in the transporting one probability measure in X space to another probability measure in the Y space, nu. So this is actually so-called the transportation map is T here. The goal is actually making the cost of transportation as small as possible. In fact, this is actually this transporting measure is so-called the push-forward operation. This is transport map, and this is original probability measure mu, and this is mu. In fact, the optimal transportation, in order to actually, before I talk about the optimal transportation problem, we need to actually discuss about this push-forward measure a little bit more. This push-forward measure is actually very similar to the, you can think about the random variable. Random variable, you actually calculate the probability distribution of the random variable. You need to actually calculate the pre-image, and that domain, the probability distribution is actually given as a probability measure of the random variable. In fact, this is the same. So you can understand in that way. Now, given that one, so original optimal transport problem by Monge is actually formulated in this way. So we are now, this is a transportation cost. Now we are minimizing the transportation cost under the constraint that's new transported. This is actually push-forward measure with respect to original probability distribution. However, the problem of this one is difficult to solve. The reason for that is this push-forward measure, push-forward operation is nonlinear, which is actually difficult to impose in the real application. So because of that, there is a very famous formulation based on the Kantorowicz, and Kantorowicz formulation is actually a relaxed version of optimal transport problem by allowing the mass splitting, or people call this one is a probabilistic optimal transport. The formulation is like this. So here, this is a transportation cost here. Now, we are now minimizing, we are now calculating average transportation cost with respect to joint distribution here. Now, the goal is to find the joint distribution among all possible joint distribution, which is satisfy this marginal for each measurement, marginal distribution. You try to find the minimum joint distribution such that this average transportation cost is a minimum. That's actually the, it turns out this joint distribution defines the optimal transportation map. It turns out that the discretized version of this one leads to the linear programming. So that's actually the invention of the linear programming. And because of that, Kantorowicz got the Nobel Prize in economics. And another nice thing about the Kantorowicz formulation is it actually allows the dual formulation. So Kantorowicz dual formulation, now original problem is with respect to joint distribution, but in the dual formulation, you are now with respect to the marginal distribution, but there is another new kind of concept, so-called counteractive potential. This is actually now minimized, try to maximize with respect to counteractive potential. And also there is a so-called seed transform here. This is actually given in this way. The calculating of seed transform is a little bit of interesting stuff. We'll talk about that a little bit soon. But now the nice thing about the dual formulation is now minimization problem with respect to joint distribution is a little bit more complicated. But now this problem is now finding the counteractive potential with respect to marginal distribution. This is easy to calculate. So because of that, this is a many advantage. Now, given this one, for example, let's go back to the Wasserstein matrix, which is represented in this way with respect to joint distribution, and you're minimizing the finding the joint distribution. Now, using the Kantorowicz dual formulation, you end up with this kind of form. But now, you mean the seed transform is now minus bar phi here. But still, this is actually the simplest thing for the seed transform. But still, you need to actually impose that as long as this satisfies the one Lipschitz constant, you can actually see this is correct dual formulation. Now, based on this one, it turns out that WGAN architecture is actually minimizing the Wasserstein matrix, and it ends up with this kind of formulation. This is a discriminator, which corresponds to Kantorowicz potential. Now this is a generator, which is transporting from the noisy to this one. Now, as I mentioned, this discriminator should satisfy the one Lipschitz condition, so we need to actually impose these penalties here. Okay, now based on this understanding, you can actually understand the popular description and analogy of the GAN from optimal transportation point of view. For example, here, the thing is now there is a counterfeit here is try to make the fake money, but police try to detect it. Now, by competing each other, we know that this become more realistic. Now, it turns out this counterfeit is a generator, or it is a transportation map. And discriminator is the copy is a discriminator, or in the alternate transport literature is a contributive potentials. Okay. So based on this kind of mathematical background, we actually in a paper we actually try to understand the geometry of a CycleGAN architecture. It has a very interesting geometries here. Now this is again the same picture for the unsupervised learning we mentioned here. Now this is an inverse solution path, and now this is a fold physics. Now here the fold physics, depending on the inverse problem, this can be known or partially known or totally unknown. So as I mentioned, we are interested in minimizing the distances. And as I mentioned, we are interested in minimizing the distances using the Wasserstein matrix because it has many advantages. Now, one of the distance between mu set and mu is now given in this way as a Wasserstein one norm here. On the other hand, distance this one and this one given in this way. But one of the tricky difficulties now the joint distribution to minimize this and joint distribution to minimize this can be different. But our goal is to finding the same joint distribution to actually minimize both of them together. So in that case, this is not the correct picture. So the best thing you can think about is now you are just adding them together and then finding the joint distribution to minimize this average cost together. In that case, it turns out if we find the dual problem of this, we can show that the dual formulation of this one is lead to the CycleGAN architecture. So there is a cyclic consistent term and discriminant term. Cyclic consistent term has given in this way. This is the G theta, and phi is a fold measurement, which is given in this way. And the other opposite equation, phi phi and G theta, and y is a measurement. As I mentioned, this phi, depending on the fold operator, it can be just a neural network or partially known small neural network, or maybe some of the if it is completely known, this is determinist cases as well. And discriminator is coming from the Wasserstein matrix, so it actually satisfies the one Lipschitz constant. Now, based on this understanding, let's compare the CycleGAN versus the penalty square we actually discussed as a classical approaches here. Now, CycleGAN architecture in the primary problem is now minimizing this term. This is in fact a data fidelity term. And in fact, this is an inverse path regularization term. So this is similar to the original penalty square. This is a data fidelity term. And instead of the inverse regularization path, we are now having a regularization term. But there's a very interesting differences between the two. The thing is, now, here this is actually minimizing with respect to one particular regularization. But on the other hand, in this case, this is minimizing with respect to the joint distribution. So it turns out that this is now finding one particular solution. Now we are finding the joint distribution to minimize this. That means it turns out that CycleGAN can be considered as a stochastic generalization of penalty square, because we are now considering stochastic mapping rather than just finding one single variable. Okay, based on this kind of theoretical understanding, we talk about several applications of this one for various inverse problems. Let's think about the multi-phase cardiac CT denoising problem. As I mentioned before, here in the dicer phase is usually low dose images, and the sister phase is low dose, and dicer phase is high dose images. But we cannot utilize this one as a reference for the supervised learning. So we have a set of data for the low dose and set of data for high dose. Now the problem here is now from the low dose to high dose, this is an inverse operator neural network, but high dose to low dose generation itself is actually noise generation is a very complicated process, especially in the CT. So we are not quite sure about the actual physical model. So we are now implementing this one as a neural network as well. Then in that case, we end up with this kind of standard CycleGAN architecture. And this is some of the result. So this is unsupervised learning without matched data. So with the 5% noise doses compared to the high dose, now this is the input image, very noisy here. Now this is target image. As you can see here, the image is different because heart is moving. Now, using this kind of unsupervised learning using the CycleGAN architecture, you can clearly see that all the noises are completely removed. And also, if you see the difference images, you don't see the structure changes, only noise are removed. And we actually did conduct with the ablation study. For example, if we just use the standard GAN architecture in this way, yeah, the result looks very nice. But however, there is, if you compare this image versus this, there is some kinds of weird artificial architecture coming here, structure coming here. So this is not good for the medical imaging purposes. If you see the difference image, there are a lot of deformation. And also, for example, another losses we actually had. But now if you actually do the proposed method, basically the difference image between this and this is just like a noise images. So that means the structure doesn't change it. Same thing here. One of the things we actually conducted is now sometimes input image sister phases, because it's not sister and the laser phase is not perfectly matched to each other. So because of that, sometimes it can be high dose. Now, if we put the high dose here, then originally you shouldn't expect any kind of thing happen. So as well as you can see in our proposed method, there's nothing changed. But in the GAN, you can clearly see the deformation here in this example. So that means CycleGAN architecture with the correct design of a neural network, we can guarantee that no artificial feature appears in this example. Now, this example is the convolution microscopy example. Here, one of the nice things is forward pass is simple. Now, usually the convolution forward pass in the microscopy is based on the point spread function. So this is a simple linear layer. But the other pass is actually the neural network. So because of that, if you compose of this kind of neural network architecture, there's a one neural network here, but this is a simple linear layer. Because of that, this is a simple, so you can easily train this neural network. If there is a multiple neural network here, CycleGAN training is quite complicated, but this is the linear layer, so it's easy to train. So this is example. This is a blurry measurement, and this is the proposed CycleGAN architecture. You can actually compare to the other competing method. You can actually clearly see the much more high resolution. Even compare with the standard CycleGAN architecture with the two neural network, we can actually have a much more higher resolution images, as you can see here in this example. Now, this is another example for the accelerated MRI. So we have a downsampling the image. So now for the operation, is a deterministic because we know the downsampling pattern here. Now, and also this is actually the forward pass, and this is the inverse pass. Because of that, the forward pass, we don't need to actually optimize at all. This is just deterministic. So because of that, the discriminator doesn't need to compete. So we have just one discriminator. And based on that, you can actually train this kind of CycleGAN architecture. Now, this is some of the example. This is an input image, and this is supervised learning. And this is actually the conventional CycleGAN with the two neural network. You can see there are still remaining artifacts, as you can see here. But now, using our proposed optimal transport-driven CycleGAN architecture, you can clearly see the much more significantly improved, and which is even comparable with the supervised learning approach. Now, based on this understanding, we are actually given some kinds of extension of this architecture for several kinds of interesting problems. So this the thing we are going to talk about is three topics. The first thing, before we talk about what we call the beta CycleGAN, we talk about we review the important generative model in the machine learning literatures, which is so-called the variational autoencoder, or VAE. So variational autoencoder idea is like this. We have an unknown image, you have an image measurement X, and now you are encoded this one using the latent variable, latent space, but during that time you are adding the noises here. Now from this latent space vectors, we are now generating the image X. Now the goal is to making this one and this one small as small possible, but still by changing this noise, you can actually manipulate, you can change this one. For example, you can actually rotate the faces. Okay, you can do some kinds of variation of the outputs by controlling this noise. It turns out this variational autoencoder is minimizing this kind of loss function, so-called the error loss function. But it turns out the error loss function composed of two terms. This term is actually likelihood term, in fact, for the generated images. And this is a Ki divergence, which is actually, in fact, latent space distances as a divergence measure. So this is actually the geometry of variational autoencoder. For example, here, this is actually the sample space here. From here, you are using the encoder to convert to the latent variable C3 here. And now C is actually the Gaussian distribution. So from here, you are now generating using the decoder to the distribution in the image domain. And it turns out that they are measuring the distance in the image domain as an L2 distance, sample by sample distances. But on the other hand, in the latent space, they measure this one using the Ki divergences. That's actually the geometry of variational autoencoder. But what happens is, this is nice, as I mentioned, that by changing the variational autoencoder random variable in the G, you can actually rotate these images, as you can see here, from this far and to another part. But interestingly, at this file, this column, which is supposed to look front, but there is a variation of these kinds of face directions. So to address this is actually, that means the feature space is not completely controllable. So this is actually what people call the entanglement. But to make this one as a controllable, people try to find the disentanglement method and the beta VAE. What they found, the solution is like this. So this is a distance in the original the sample space, and this is a distance in the Ki divergence in the latent space. Now they actually add some more weighting parameters in these kinds of distances. By having a big parameter, you have a more weight on the distances in the sample space. Now, as you can see here, we have a much more controllable latent space, which is disentanglement, feature space disentanglement. So we have now in this column, everything is just loop front, okay? But now if you compare this one versus this, the image quality of this one is better than this because we have more weight in the latent space. So that means less weight in the image space. So now based on this kind of things, we can actually think about the different kinds, extending this one to the CycleGAN architecture. Especially, our goal is actually applying this one for the matter architect reduction problem for the unsupervised manner. So here in the white space is matter artifact images, as you can see here. Now, y-axis is artifact-free images. Now, as I said, in the CycleGAN architecture, from here to generator generating artifact-free images, and this one is generating matter artifact images. In fact, to learn this part of the images, you need to actually, the neural network should learn the matter artifact generation physics, like a beam hardening or photon starvation, and etc. But usually the matter artifact generation process is highly complicated. So because of that, the learning this one is a little bit more difficult. So the focus here is now we are generating the artifact-free images. So why we are focusing here? So the goal is now we are doing the less emphasis weight in this domain. And then instead we are doing the more focus in the artifact images. So now this is original distance measure. Now we have a 1 of beta parameter. If beta is big, we have a less focusing on the artifact image generation process, but more focusing on the artifact-free image generation process. Now, from this kind of primal problem, if you actually formulate the dual formulation, you end up with this kind of another CycleGAN architecture. But we have a very interesting observation here. Now, 1 of beta parameter is now only in this explicitly shown the CycleGAN, cyclic consistence term, but it's not explicitly shown in the discriminant term. And also, it turns out that other than the CycleGAN term, this is actually the same neural network architecture, the CycleGAN architecture. But one important thing you can actually see here is now, because of the beta term, the discriminant term need to be 1 of beta ellipse constants instead of 1 ellipse constant. But usually in many of the form of the CycleGAN, many of the regulation term to make this ellipse constants is usually the constant its value itself doesn't matter too much. So that means we can actually use the same kind of discriminant architecture. Furthermore, we actually impose another component to actually improve the accuracy of this matter artifact reduction. So usually matter artifact is localized in some special domain. Furthermore, what happens is in the matter artifact domain is actually radiated from some of the sparse locations. So that means it's better to actually focus on those kinds of matter artifact region rather than other things. So in order to do that, we actually add some kinds of attention mode, spatial and channel attention. So this using so-called the CBAM unit here, in this kind of unit architecture with the SCIC connection, we actually add a CBAM unit, which gives a special channel attention in specific channel, as well as special locations as well. Now, this is a result. This is a matter image. And we don't, as I mentioned, this is unsupervised learning. You don't have any matched reference data. Now, this is a linear interpolation, the classical approaches in the computer tomography literatures. You can actually see that blurrings here and the matters are gone, and still some of the still remaining artifacts. And this is a famous algorithm in the literatures using the normalized matter artifact reduction algorithm. Still, you can see the remaining artifact, especially in this kind of data image. But now this column is actually based on our beta CycleGAN architecture. You can clearly see this kind of pattern artifact is removed and still matter is retained. Furthermore, one of the difficulty in matter artifact reduction is not only this matter region, but the region, homogeneous region between the matter is difficult to recover. For example, MR, there is still streaking artifact you can see here, but now from our method, you can clearly see that streaking artifact is significantly reduced. Furthermore, another thing about our network is now if actually the matter is small or the metallic artifact is very minimal, or the non-metallic part is given as a network output, our method doesn't, this is a difference image, doesn't actually alter the image at all, similar to actually we discussed in the cardiac denoising image cases as well. But now this column is actually another unsupervised learning method for the matter artifact reconstruction, which is so-called disentanglement network. But still, you can see that they actually change the images. And same thing, CycleGAN and also NMAR, and there is still remaining the images are a little bit blurry, but those kind of things is completely gone in this kind of beta CycleGAN architecture. Now, another extension you can think about is a multi-domain CycleGAN architecture. Here, this is actually coming from the ultrasound application. Ultrasound images usually based on the beamformers, we have a DAS images. Then DAS images are usually blurry and also has a lot of speckles here. So people, depending on the application, some people are interested in deconvolution, or some people are interested in despeckling. But if actually do the CycleGAN based actually the image transfer, of course, this is also unsupervised learning. We need a two CycleGAN architecture, two generator. One is converting to the deconvolution image, and the other is to converting to the speckle removal image. But our goal is actually to utilize this to actually same network architectures to actually generate the two images depending on the choices. In fact, this problem looks very similar to so-called the StarGAN architecture in the machine learning literature. In the StarGAN architecture, what they do is a very similar approach. We have a domain one to converting to any domain. But however, it turns out, we show you the result later. This is actually overkill, I would say, for the ultrasound imaging. The reason for that is usually ultrasound start with the DAS images, and from the deconvolution image, you don't need to generate the DAS image at all. So that means the passage, the signal reconstruction passage is all asymmetric. But StarGAN need to be actually symmetric. It can generate anything from any domain. So because of overly complicate this one, and StarGAN training is a little bit more difficult, and because of that, it does not generalize well compared to this kind of architecture. Now, in order to actually design this kind of architecture, we need to go back to the original geometric pictures again. Here, now this is actually the DAS images, and with the real DAS measurement, we are doing the generating here, and with the generator. Now, the thing here is now, as I mentioned, in X domain, there is these speckle images and deconvoluted images with the blue and red images. Now, then algorithm, this is a cascade measure. Now, from generated images, algorithm actually we are now converting to a binary domain such that this mapping to this, the transport from here to here is now satisfying this kind of original distributions here. That means we need to actually have 4 different kinds of distances. This one is a distance between this domain, and this one is distance between this domain. Now, this is a distance from this distribution to original distribution C here. And this is actually synthesized distribution and original distribution as well here. Now, as I mentioned, this is actually, it's better to utilize the Wasserstein matrix for this domain. But here, this is a discrete domain. In that case, the KI divergence is much simpler. And furthermore, if actually utilize the KI divergence, only parameter depending term itself is actually the cross correlation term here. So we have a Wasserstein distances here, and then classification the cross correlation cross entropy dependent term here. Now, if we convert it to the dual problem, again, this is cyclic term, consistent term, and discriminate term, and coming from the one Lipschitz penalty, and there's 2 terms here. It turns out this is a classification losses. So based on that, on the architecture, you can design this one is like this. We have a generator here from the DAS image to the target domain, and target domain to the DAS image. But now target domain is multiple, so we actually have a mask vector to guide this one is which going to which target, the convolution or the speckle image. And from the target image, it always need to go back to the DAS images. Now from the discriminator setup, now target images from DAS images, we just need a discriminator here. But now we actually have also discriminate whether this is true target image or not. And furthermore, we need actually the classification loss here. And because of that, we need the classifier here for designing whether this is the convolution image or this is speckle image, classifying that one. And that can actually share the, some of the part can be shared, but head can be different. So this is actually the architecture here. Now this is example, this is DAS image. And now from here, you are converting to the deconvolution domain. This is a supervised learning method, and this is this speckle domain. You have another network to the supervised learning method. And CycleGAN need the 2 kinds of network architectures here. StarGAN is similar, but as you can see here, the convolution image is not as good as a proposed method compared to this. Ground truth, same thing happened. So if actually utilize a StarGAN, which is overkill compared to application, in that case, the performance is not good. But however, using this kind of multi-domain CycleGAN architecture, we have a much better image, which is close to the original ground truth images. Now, final extension we are talking about is actually wavelet directional CycleGAN architecture here. The idea is following. Most of the people think that CycleGAN should be implemented in the image domain. But however, knowing that this is actually just like a converting 2 property distributions, it's better to actually converting the property, converting the image signals in some domains such that converting the transportation problem is much easier. So this is the main idea. For example, this is a satellite images from the satellite imagery. There's sometimes this kinds of vertical noise artifact, and or like across the random, the horizontal kinds of artifact here. Now the goal is instead of utilizing this one image as an input for the neural network, because sometimes if we do that, you can actually the original image itself can be also altered, or maybe some blurry or become blurry. So instead of doing that, we are just like converting to the neural network to extract the noise dominant bandit. For example, here from this kind of wavelet decomposition, if we just extract this part of horizontal component and then doing the inverse transform, you can actually do that noise dominating image signal. Same thing, noise dominant image signal. Now the goal is now doing the optimal transport in this domain. So here, this is actually what happened here. From the noise, we are learning the mapping from the horizontal wavelet directional image to the noiseless wavelet image, which is unmatched. And based on that one, we can actually estimate the noise component. This is what happened here. Same neural network architecture, but everything is now implemented in the wavelet directional residual images. Okay. Now this is an example. This is a real data from the real satellite imagery. So this is actually the true measurement from the satellite sensor. Now you can see this kind of artifact here. The supervised learning is not possible because we don't have any ground truth. If we actually utilize the conventional classical approach, like this is actually coming from the BM3D or all other method, and you can, and also you can clearly see our method is outperforming and compared to other methods. And in fact, this is actually our collaborator in the Korean version of NASA, they actually have a very sophisticated algorithm to actually eliminate this one. So it looks like yeah, in that case, this is a commercially available solution. So that can actually looks actually very similar to here. But this is actually not learning-based approach. But now, one other thing you can actually clearly see here is advantage is the cloud cases. This is actually from the real cloud. Now, all other methods, even actually the commercially available sophisticated algorithm, still there is a limiting string artifact, but this unsupervised learning using the CycleGAN architecture in the wavelet-domain completely remove it. Now, this is ocean data for horizontal noises, as you can see here. Now, this is actually the simulated data. We have real images, and from images, we add this noise pattern. So we know the ground truth. Now, this is actually our recovered result. You can clearly see that you can actually have a correct result compared to the ground truth here. But now all other maths are still remaining the remaining noises, or maybe some of the vessels, some of the actually the real structure can be damaged as well. This is actually the real measurement. There is no ground truth here. Now this is our method. There is all the remaining method. There is a still remaining artifact here, but still we actually have a significantly reduced artifact. In summary, so as I mentioned, unsupervised learning is actually a very important topic in the image reconstruction for inverse problem. And our theoretical finding shows that optimal transport is a very important mathematical tool to design unsupervised neural network architecture. And also, cycle can be derived by minimizing two Wasserstein distance in the input and target space. And based on that, you can do a lot of various extensions. And so this kinds of geometric view can be actually generalized for other kinds of neural network design as well. With that, I'd like to conclude my talk. Thank you very much for listening.
Thank you, Jong. I think that's a really wonderful talk. And I think we do receive some questions. But actually, before going through that, I myself have some questions. I mean, I also, interested of this kind of CycleGAN, also especially the interpretation you provided. So I think that's interesting. So Jong, can I ask a question about this interesting interpretation of CycleGAN, which you actually treated as, treat the backward process as something like a regularizer in solving inverse problem, right? My understanding is that this kind of learned reverse process is kind of totally data driven. I mean, it can be a neural network type, which is very flexible. But on the contrary, for solving inverse problem, normally the regularizer is based on certain prior, like say sparsity or low rectness. So how do you view this two? Because it seems like sometimes the flexibility can be good, but sometimes, maybe due to overfitting or some kind of non-idealness of the data, it can be, doing something bad. So is there any analysis between the so-called the model-based regularizer versus this kind of data-driven approach? Or do you find anything particularly interesting comparing these two approaches?
Yeah, actually, that's a very excellent question, actually. That's actually the one thing I wanted to emphasize in this talk. Here, this is actually our framework to understanding CycleGAN is also variational approaches based on the minimizing the distance or energies, right? But now in the most of the cases, this kinds of energy is coming from the data. In fact, actually, this is actually data matching term here. But usually the inverse solution regularization term is actually coming from some prior information, etc. But here our view is, instead of doing that, and because this is an unmatched problem, so match the distribution. So now we need to actually think about the variational problem in the probabilistic sense. So that means you need to actually minimize the probability distribution, statistical distribution in the measurement domain, as well as in the image domain at the same time. It turns out that it gives a very interesting regularization term for, as a inverse path. And not only, but still, it's, in this sense, I would say it can be actually interpreted as a regularization term, but also it can be said, this is actually, in fact, actually just like minimizing two domain, because actually if you want to do the matching to the distribution, it's better to actually minimize in both paths anyhow, right? So otherwise this distribution and this distribution cannot be aligned. So this is actually the natural way from this kind of geometric view. This is a natural way to derive this problem, this kinds of distribution matching problem in two different domains. So in that sense, regularization to me is more like asymmetric. We have a regularization term is, this is actually one of, I go to the here. Regularization term is usually like this, maybe here, this is small compared to the length, for example. This is not symmetric. But here now, because we are now minimizing the two distribution at the same time, so this becomes a symmetric problem in the data domain as well as the measurement domain. So that's actually one of the nice insight we can actually obtain here. But still, this works as a regularization term in the sense of the PRS.
Yeah, I think that's a very pretty interesting insight. I mean, also unique. So, and I see a lot of papers are still on archive. So definitely that's very new, and people can actually further develop that, because that's kind of different from the classic view, like people view this kind of CycleGAN. So right. I think it's really unique. Okay, I think we.
Question.
Oh yeah, Sai, go ahead.
So Jong, so at testing time, once you learn the CycleGAN, at testing time, the process, is it single shot? You take the measurements and you apply the network G theta.
Yeah, that's a very excellent question. Yeah, I forgot to mention it. In fact, one of the nice thing about this one is now this, once, for example, here, once your neural network is trained, this is just, you don't need anything. You just need one generator. This is feed-forward neural network. In fact, it turns out this all these kinds of complicated architecture is just like a wrapper, I would say, for the training purpose. But once training is done, you only have a feed-forward neural network. So that's actually one of the nice things about this kind of CycleGAN-based architecture for the unsupervised learning. For example, if you think about the deep image prior, you need to actually solve the optimization problem. That's complicated. Or if you actually do, for example, like other method using like, some other method, but most of the times you need to actually solve some kinds of like complicated solutions, even in the inference time, test time. But here, one of the nice things about the CycleGAN architecture is, once you train it, then you can actually forget about everything. You just need one generator, then that's it.
I think that's a really good advantage of the CycleGAN architecture, Jong. Yeah. But conceptually, I wonder, like, so having sort of a more complicated structure at testing time, such as, using an iterative method with a data fidelity term, or using the unrolled method like BCDNet or ADMMNet, or these approaches, or plug and play. And so there seems to be some pro and con. In the con is that it's more expensive. So with CycleGAN, it's much simpler at testing time. But is there something perhaps to gain by having still the more rigorous data consistency and architecture at testing time, although you lose computationally?
Yeah, actually, so that's actually I mentioned before. Actually, one of the nice things about this kind of plug and play or the model-based approaches, the network, you don't need a lot of training data to train the network.
Right.
But here in the CycleGAN, even though it's unpaired, unsupervised learning and unpaired data, still you need the data much more than those kinds of like plug and play approaches. So one of the nice things about the plug and play and model-based approaches, your network can be simple, and then actually you need less data. But in that case, that's ideally suitable. But if you actually have enough data, but we don't have any matched data, I think the CycleGAN, one of the nice things about the CycleGAN approach is once it's trained, it's feedful, it's much simpler and straightforward. You don't need any kind of additional optimization algorithm. So that's one of the advantages of the CycleGAN. So depending on the training scenario and depending on the application, it's actually, there's a pros and cons in both approaches, like that, I would say. But one of the nice thing about, I want to say is actually, for example, one of the nice thing about the plug and player compared to the feedforward, standard feedforward image domain network is they actually incorporate the physics during the inference phase, right? As a data fidelity term. Now in this kind of optimal transportation-based CycleGAN architecture is, we are now incorporating physics during the training phase. So both approaches can be now incorporate the physics. That's actually the good thing about this, yeah.
I think that's a very good insight, Jong.
Yeah.
My one final question is, so with regards to comparing this to other unsupervised methods in the literature, right? So deep image prior is one, and there are also other, like some, other previous methods, dictionary learning and others. So do you have some insights or some recent thoughts on perhaps, because these methods, they don't use the extensive amount of training data that CycleGAN uses, perhaps that gives CycleGAN some immediate advantage, would you think?
Yeah, I think it's similar to the, I think a similar thing. For example, in these dictionaries and those kinds of supervised learning methods, is one of the big advantages is you need less training data, even no training data, right? But still, CycleGAN need the training data, even though it's unmatched. So that's actually the big difference. So as I mentioned, that application might be different depending on different type of unsupervised learning method.
Sounds
but
good.
in most of my application we have in mind, actually especially in the medical application, I think that quite a lot of scenario we have enough data, but they are not matched. So in that cases, this kind of CycleGAN architecture is one of the nice direction to pursue. That's actually my insight.
Thanks, Jong. A great talk. I really enjoyed it. Thank you.
Thank you. Thanks, Cy, for the excellent questions. So perhaps we can, walk through other questions from the audience. So by the way, for the audience, if you have any questions, feel free to leave them at the Q&A session so we can go through the question from you guys. I think the first two questions are both from Sharath. So I don't know whether Sharath want to kind of ask yourself. I actually allow you to speak. So if you want to speak, you can unmute your mic. Otherwise, I will just read the question for you.
Hello?
Yes,
Hello?
we can hear you.
Okay, yeah. So my first question is, I think there's it's a very informative talk. Quite a lot of different CycleGAN architectures were presented, but I was just wondering which CycleGAN amongst those that are presented have you found to be the most optimal when it comes to denoising and removal of image artifacts?
Okay, so that's a very important but tricky question. Yeah, in fact, actually, the GAN has a lot of different versions depending on what kinds of discriminant architecture people use. And also, even in the GAN, the standard GAN and CycleGAN is different. And also inside of the GAN, for example, even for the, there is a star GAN, or there is all different kinds of GAN architecture for multi-domain transpose as well. So depending on which scenario you are choosing, then that's actually, depending on that one, that's actually, you can choose a different kind of thing. But for example, if you just do the unsupervised learning method for the denoising and image artifact removal, I think with the CycleGAN architecture and with the discriminator with the RSGAN laws, or maybe the gradient penalty laws is actually quite robust in our experiment. So we usually end up with these kinds of architectures.
Okay.
I think, Shras, you have another question you want to ask? I think the
Yeah,
second question
so
also come from you. Yes, go ahead.
yeah. So I was also wondering about the CBAM module that Prof. Jong was mentioning about with regards to the attention-guided beta cycle GAN. So I was wondering whether this CBAM module needs to be trained on its own for individual channel. So for example, if you have a color image, do you need to spectrally deconvolve it and then do separate training for this CBAM module, or is it just an immediate plug-in kind of a module?
Okay, so in our cases that we medical imaging, there is no color channel, so we can actually use the gray label. But however, CBAM module is now inside of the SCIC connection. That's already multi-channel. But we actually we just use the CBAM module as it is, but everything is trained at the same time. So actually the parameter for the CBAM and also neural network weight is also backpropagated at the same time during the training. So it doesn't need to be separated trained.
Yeah. Thanks a lot for your answers.
Thank you. Thanks, Shreyas, for the great question. So I think next question is not quite about the talk. It's about I think Ben Xuan Wang is asking whether we are issuing any certificate to prove attendance. I mean, I don't think we're doing this for now because this is more like a free and open webinar for all the attendees, students who are interested. Except that we're doing this for some partners, like we have some student organization partner with us. But perhaps in the future, if we see a high demand from the audience, we can consider that. But unfortunately, we're not doing this for now. But perhaps we can discuss that, to follow up with this issue. Okay, so I think the next question is from anonymous attendee. So then I just read the question myself. So the attendee is asking, could you give us a sense of how much training data this method required and how many parameters are being learned here? I think that's talking about the CycleGAN works.
Okay.
But I'm not sure which one, because John mentioned several works.
Yeah, so, okay. So exact number, I should ask my students. But however, rule of thumb is actually usually, and also how many parameters usually depending on the neural network architecture you use. In our cases, most of the time, the generator model, we use a unit type architecture. So the number of parameters for each generator is about the unit architecture, but we need a discriminant architecture. And discriminant architecture, we use popular GAN architecture. So number of weight is basically determined that way. But in terms of training data, I think several hundred at least, I guess. So several hundred for each domain at least. But the thing here, nice thing about this one is actually, this is an image domain, image by image train. So each slice of each sample, for example, is actually a separate training data. So for example, CT image for the AAPM data, so there are several hundred of slides for each patient data. So that means if you have a 10 patient data, you have already more than 1,000 data. I think that's actually quite pretty much enough for our purposes. Yeah.
Great. Thanks, John. I think we have another question. Oh, this is from Fan. Oh, I'm not sure whether is it Fan Lam from UIUC. So perhaps Fan, do you want to ask a question yourself? I actually allow you to speak. So if you wish, you can unmute and ask.
Bihan, I think he also mentioned in the chat that his mic is not working.
Oh, okay. Sorry, I didn't check the. Okay, then I will just read the question for Fan. So he's asking if I train this type of CycleGAN on one contrast, say T1 weighted images, can it be applied to T2 weighted images as well?
Well, if actually you can actually design a CycleGAN from T1 to T2 weighted images as a conversion. That's actually many people are trying. But if actually want to do the denoising for the T1 and T2 images at the same time, one method is you can actually mix the data together as an input, and maybe with noise data as an output as well, and then train them. That could be one method. But we actually didn't, we didn't actually combine the T1 and T2 at the same time, most of the cases. So, well, I'm not sure whether this is really working or not, but you can try. Yeah.
Great. So I hope that clarified the questions. All right. So is there any other question from the audience? Okay. So if not, perhaps we can wrap up today.
Okay.
So let's thank Jong again for the wonderful talk, and also I think we need to give a kind of a advertisement for our next talk, right? So this space webinar will be a bi-weekly event. So the next talk will happen in 2 weeks, which will be the next week, and the speaker will be Orazio from NVIDIA. And I think the talk is about RGBD images fusion and processing. So welcome to come back and rejoin us for the next webinar. And also thanks John for the wonderful talk, and hope you all enjoy it. Yeah, that's it. Thank you so much, and that's it for today's talk. Thank you.
Great, thank you much.
Thank you.
Bye-bye.
Bye-bye.